Everyone thinks finding an Earth 2.0 is just a matter of time. They're wrong. The popular notion of a Goldilocks zone, a perfect orbital distance where water can exist as a liquid, has dominated our search for life beyond Earth. It's a compelling, intuitive idea, but this seemingly simple concept hides a universe of complex variables that dramatically shrink the true habitable real estate available to life. For decades, our telescopes and probes have been scanning the cosmos for these just right worlds. We've found thousands of exoplanets and a significant fraction orbit within their star's theoretical Goldilocks zone. On paper, these are prime candidates. But what if the paper is missing most of the story? The simple Goldilocks definition overlooks a critical truth. Habitability isn't just about water. It's about a delicate, intricate interplay of planetary characteristics, stellar behavior, and even galactic environment. Many of the worlds we've enthusiastically labeled potentially habitable are, in fact, incredibly hostile. Consider our own Earth. It sits comfortably in the sun's Goldilocks zone. But what truly makes Earth special isn't merely its distance from the sun. It's a confluence of factors, many of which we're only beginning to appreciate, and few of which are guaranteed for any given exoplanet. One crucial factor is a planet's size. Too small like Mars, and it can't hold onto a thick atmosphere or sustain a molten core, which is vital for a magnetic field. Too large, and it might become a mini-Neptune, a gas giant with no solid surface, or experience crushing gravity. Then there's the magnetic field. Earth's molten iron core generates a powerful magnetosphere, a protective bubble that deflects harmful solar radiation and prevents our atmosphere from being stripped away. Without it, the Goldilocks zone becomes a death trap of cosmic rays and stellar winds. Atmospheric composition is another major player. A planet might have liquid water, but if its atmosphere is primarily toxic gases, or too thin to trap heat, or so thick it creates a runaway greenhouse effect, life, as we know it, simply couldn't survive. Venus is a stark reminder of this. The star itself matters profoundly. Most stars in our galaxy are M-dwarfs, smaller and dimmer than our Sun. While they have long lifespans, planets orbiting them in the Goldilocks zone must be incredibly close, often tidally locked, meaning one side perpetually faces the star. This tidal locking creates extreme temperature differences, one side baking hot, the other perpetually frozen, with fierce winds raging in between. While some scientists theorize eyeball planets or Terminator zone life, it's a far cry from the stable environments we see on Earth. Furthermore, M-dwarfs are prone to violent flares, bursts of radiation that could sterilize a close-orbiting planet, stripping away any nascent atmosphere or sterilizing its surface. Even within the Goldilocks zone, habitability is a fleeting prospect. Let's not forget plate tectonics. Earth's shifting crust recycles carbon dioxide, regulates global temperatures, and creates volcanic activity that releases essential gases. Without this geological engine, a planet's climate could become unstable, leading to runaway ice ages or greenhouse effects. And the moon. Our moon plays a vital role in stabilizing Earth's axial tilt, preventing drastic wobbles that would cause extreme climate shifts. Without such a large, close companion, a planet's seasons could become wildly unpredictable, making long-term habitability incredibly difficult. Even the presence of gas giant neighbors, like Jupiter, is crucial. Jupiter acts as a cosmic vacuum cleaner, deflecting comets and asteroids that might otherwise bombard Earth, reducing the frequency of extinction-level events. Not every star system is so fortunate. The galactic environment also matters. Our solar system is located in a relatively quiet region of the Milky Way, away from the chaotic, radiation-filled galactic center. Planets in busier, more active regions might be constantly bombarded by supernova or gamma-ray bursts. So when we hear about thousands of exoplanets in the Goldilocks zone, it's important to remember this. That zone is a necessary condition, but far from sufficient. It's the first filter in a long, complex series of requirements for true habitability. The paradox is this: the more we learn about what makes Earth truly habitable, the rarer true habitability appears to be. Each new scientific discovery adds another layer of complexity, another constraint that drastically narrows the field of potential Earth 2 zeros. This isn't to say life is impossible elsewhere. Far from it. The universe is vast beyond comprehension, but it does suggest that life, particularly complex, multicellular life like ours, might require an incredibly specific, finely tuned set of circumstances. The search for truly habitable worlds, therefore, goes far beyond simply locating a planet in the right orbital band. It requires sophisticated spectroscopic analysis of exoplanet atmospheres, precise measurements of their mass and density, and a deep understanding of stellar evolution. Future missions, like the proposed Habitable Worlds Observatory, aim to directly image Earth-sized exoplanets and analyze their atmospheres for biosignatures, chemical indicators of life. These will be our best tools for truly testing the Goldilocks paradox. The journey is long, and the answers won't come easily. But each step, each new insight into the intricate dance of cosmic forces that allow life to flourish, brings us closer to understanding our place in this immense, enigmatic universe. Perhaps the greatest lesson from the Goldilocks paradox is a renewed appreciation for our own planet. Earth isn't just habitable, it's a miracle of cosmic engineering, a testament to the incredible unlikelihood of our existence. It forces us to redefine what habitable truly means, pushing us beyond simplistic definitions to a more profound, nuanced understanding of the conditions necessary for life. And in that deeper understanding lies the real frontier of discovery. To explore more untold stories of cosmic discovery, watch our deep dive into the Great Filter Theory next.